People often ask me what quantum mechanics really means, and I always tell them the same thing. If you think you understand quantum mechanics, you haven't understood it properly. That's not false modesty. That's an observation about the nature of reality itself. Because what we discovered in those early decades of the 20th century wasn't just a new theory about atoms. It was a revelation about the limits of human knowledge, about what can and cannot be known, and about the uncomfortable fact that nature simply doesn't behave the way our intuition insists it must. Let me start with something that sounds like a riddle, but it's not. It's a statement about electricity, about atoms, about everything physical that exists. Here it is. An electron is both a particle and a wave, not sometimes one and sometimes the other, not approximately one with properties of the other. Both, simultaneously, completely, and yet you can never observe both aspects at once. Now, your mind rebels against this immediately, doesn't it? Because in our everyday world, something is either a discrete object or it's a spread out disturbance, a rock or a ripple. Never both. The opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth. And this is the most profound truth in all of physics. When people talk about electricity, about electrons moving through wires, about current and voltage and resistance, they speak as though they understand what's happening. And in a certain sense, they do. You can calculate how much current flows. You can predict what a circuit will do. You can build magnificent machines. But here's what almost nobody grasps. The electron itself, the fundamental particle of electricity, doesn't have a position or a trajectory in the way we normally use those words. It's not a tiny ball bearing rolling through a copper tube. It's not traveling along a definite path. Before you measure where it is, it genuinely isn't anywhere in particular. Not because we're ignorant of its location, but because location itself is a property that only comes into being through the act of measurement. That last sentence probably sounded mystical to you. I assure you it's not. It's the most precise statement we can make about reality at the atomic scale, and it comes from decades of experiments that gave us no other choice. Let me show you why. Consider a very simple experiment, one that my colleagues and I discussed endlessly in those Copenhagen years. Take a source that emits electrons one at a time. Put a barrier in front of it with two narrow slits. Behind that, place a detection screen. Now fire electrons at this barrier, one by one, and watch where they hit the screen. What do you expect to see? Well, if electrons are particles, little bullets of matter, you'd expect them to go through one slit or the other, and you'd see two clusters on the screen, one behind each slit. That's what bullets would do. That's what common sense demands. What? That's not what happens. Instead, you see an interference pattern. Bright and dark bands spread across the screen, exactly like what you get when waves pass through two slits and interfere with each other. The peaks of one wave add to the peaks of another, creating brightness. The peaks cancel the troughs, creating darkness. This is wave behavior, unambiguous, inescapable. So you conclude electrons are waves. Problem solved. Except now do this. Close one of the slits. If electrons are waves spreading through both openings, then blocking one slit should just reduce their intensity but preserve the pattern. But it doesn't. The moment you close one slit, the interference pattern vanishes completely. You get a single cluster on the screen, exactly where you'd expect if electrons were particles passing through the open slit. So electrons are particles after all. Problem solved again. But wait, open both slits and the interference pattern returns. The electron, this single electron that you know, went through your apparatus, because you can count them one by one, somehow produces a wave pattern that requires passing through both slits simultaneously. Yet if you try to detect which slit it went through, if you put a tiny measuring device at each opening to catch the electron, in the act the interference pattern vanishes. The moment you look to see which slit it used, it becomes a particle again, going through one or the other, and the wave behavior disappears. You see the problem now. The electron isn't misbehaving. Your concepts are inadequate. You're trying to apply ideas from the large scale, world position, trajectory, definite properties existing before measurement to a realm where those ideas simply don't apply. And this is where most people make the fundamental error. They ask, which is it really? Is the electron really a wave that sometimes acts like a particle? Or really a particle that sometimes acts like a wave? And I tell them that question has no meaning. Or rather, the question reveals that you are still thinking classically, still assuming there's some true underlying reality that our experiments are merely approximating. Here's what we learned, what all the mathematics and all the experiments forced us to accept. An electron is described by something called a wave function. This is a mathematical object that contains everything that can be known about the electron. Not everything that exists, mind you, but everything that can be known. And this wave function spreads through space like a wave, passes through both slits simultaneously, interferes with itself, and creates a pattern we observe. But the moment you measure the electron's position, the moment you interact with it in a way that reveals where it is, the wave function collapses. Instantly, the spread out possibility becomes a definite actuality. The wave becomes a particle. Not because something physical happened to the electron, but because the act of measurement creates the property you're measuring. This is complementarity. It's the recognition that you need both descriptions, wave and particle, position and momentum, energy and time. But you can never have both simultaneously. Not because of experimental limitations, not because we're not clever enough, but because nature at the quantum scale simply doesn't contain definite values for complementary properties at the same time. The electron doesn't have both a precise position and a precise momentum before you measure. It has neither. Or more accurately, it exists in a state where asking about those properties is like asking what direction purple is. The question assumes something that isn't there. Now, this probably sounds like I'm saying quantum mechanics is subjective, that reality depends on consciousness or observation in some mystical sense. That's a common misunderstanding, and it's wrong. Let me be very clear. When I say measurement creates reality, I don't mean a conscious observer is required. I mean any physical interaction that could in principle reveal information about a quantum system causes that system to behave as though it has definite properties. A photon hitting an electron is a measurement. Electron colliding with an atom is a measurement. The entire apparatus, the entire environment is constantly measuring quantum systems. And this is why we don't see quantum effects in everyday life. Not because they stop existing at larger scales, but because large objects are constantly being measured by their surroundings, constantly collapsing into definite states. But at the scale of atoms, in carefully controlled conditions where we can isolate systems from their environment, the quantum nature reveals itself. And it's not just strange. It's fundamentally different from anything in classical physics. In classical physics, particles have definite positions and velocities at all times, whether you measure them or not. The measurement just reveals what was already there. But in quantum mechanics, the measurement brings things into being. Before measurement, the electron doesn't have a position. It has a probability distribution, a wave of possible positions. And only through interaction, through the exchange of energy and momentum that measurement requires, does one of those possibilities become actual. Werner Heisenberg captured this mathematically with his uncertainty principle. You cannot simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely you measure one, the more uncertain the other becomes. And this isn't a statement about measurement technology, it's a statement about reality. The product of the uncertainties, the position uncertainty times the momentum uncertainty, is always greater than or equal to a fundamental constant of nature, Planck's constant, divided by 4 pi. That number, tiny but finite, sets the scale below which classical concepts break down completely. Think about what this means for electricity. Every time an electron moves through a wire, every time current flows, every time quantum mechanics, the electron isn't following a definite path. It's in a superposition of many paths simultaneously, and only when it interacts with something, another electron, an atom, a detector, does a particular outcome manifest. The flow of electricity through a conductor involves electrons tunneling two barriers they classically couldn't cross, existing in states that span multiple atoms, behaving in ways that would be impossible if they were classical particles with definite positions and velocities. And this isn't philosophical speculation anymore. This is engineering. Every transistor in every computer chip depends on quantum tunneling, on electrons passing through barriers by existing in superposition states that extend beyond their classical limits. Your entire phone, the device you might be watching this on, operates because billions of electrons are behaving in ways that violate classical intuition, billions of times per second. When Intel or Samsung manufactures a processor, they're not just applying quantum mechanics. They're building devices that only work because quantum mechanics is true, because electrons really do behave this way, because complementarity and uncertainty and superposition are features of nature itself. Lasers are another perfect example. In a laser, photons, particles of light, are in what we call a coherent state. They're all in phase with each other, all acting as a single wave. This is only possible because of quantum mechanics, because photons can exist in superposition states, because the wave nature of light is fundamental. Yet when a single photon from that laser hits a detector, it arrives as a localized particle, creating a single click, depositing all its energy at one point. Wave and particle. Both real, both necessary, neither complete. Atomic clocks, the most precise time-keeping devices ever created, operate on quantum transitions in atoms. GPS satellites carry atomic clocks, and they have to account for relativistic effects, both special relativity because they're moving, and general relativity because they're in a weaker gravitational field than Earth's surface. But the quantum transitions themselves, the absorption and emission of photons at specific frequencies, are fundamentally quantum mechanical. Electron in a cesium atom exists in superposition states, and transitions between these states define the second. Time itself, as we measure it most precisely, is defined by quantum mechanics. Even electricity in its most basic form, current, flowing through a wire involves quantum phenomena at every step. The ability of electrons to move freely through a conductor depends on quantum mechanical band structure, on the fact that electrons in a solid don't have individual energies but exist in bands of allowed states. An insulator differs from a conductor not because electrons are somehow bound more tightly, but because the quantum mechanical band structure has a gap that electrons can't easily cross. Semiconductors are materials engineered to have band gaps of just the right size, so that small amounts of energy can promote electrons into conduction states. Your understanding of electricity, if it's purely classical, is fundamentally incomplete. But here's where I want to be very careful, because this is where people often misunderstand what I'm saying. I'm not claiming that classical physics is wrong. It's not. Within its domain, the domain of large objects, slow speeds, weak gravitational fields, classical physics is extraordinarily accurate. We still use Newtonian mechanics to launch satellites, still use Maxwell's equations to design antennas, still use thermodynamics to build engines. The issue is that classical physics is a limit, an approximation that works when quantum effects average out, when uncertainties become negligibly small compared to what you're measuring. The problem is that people assume classical physics is fundamental and quantum mechanics is some kind of correction. It's actually the reverse. Quantum mechanics is fundamental. Classical physics emerges from it in the appropriate limit, just as Newtonian gravity emerges from Einstein's general relativity when gravitational fields are weak. You can derive classical mechanics, but you cannot derive quantum mechanics from classical mechanics. The quantum world is primary. The classical world is what happens when billions upon billions of quantum systems interact, when measurements happen so frequently and thoroughly that superposition can never establish itself, when the uncertainty principle's effects become too small to detect. And this brings me to what I think is the deepest implication of quantum mechanics, something that goes beyond physics into epistemology, into the philosophy of knowledge itself. What we learned is that there are limits to what can be known, not because we're ignorant, not because our theories are incomplete, but because nature simply doesn't contain certain answers. Before you measure an electron's position, it doesn't have a position in a classical sense. There's nothing hidden, no secret variable determining where to be found. The question, where is it, only becomes meaningful when you perform a measurement that could answer that question. And at that moment, by performing that measurement, you create the answer. This is deeply uncomfortable for most people, including many physicists. Einstein famously resisted it his entire life. He wanted to believe that God does not play dice, that quantum mechanics was incomplete, that there must be some deeper level of reality where things have definite properties even when we are not looking. He proposed thought experiments designed to show that quantum mechanics couldn't be complete, that there must be ways to measure both position and momentum precisely if we were clever enough. And every single one of those thought experiments, when analyzed carefully, confirmed quantum mechanics and refuted the classical intuition. Not because Einstein wasn't brilliant, he was perhaps the most brilliant physicist who ever lived, but because his intuition, shaped by classical physics and by a certain philosophy about how reality must be, couldn't accept what the experiments were telling us. The experiments are unambiguous. Quantum mechanics has been tested more thoroughly than any theory in history. Every prediction it makes, no matter how strange, has been confirmed. Particles really do tunnel through barriers. Entangled particles really do exhibit correlations that no classical theory can explain. Superposition states really do exist, and measurements really do collapse them. The theory isn't incomplete. Our intuition is. So what does this mean for how we should think about electricity, about electrons, about the physical world? It means we need to hold two pictures in mind simultaneously, even though they seem contradictory, when we calculate current flow. When we design circuits, when we think about electrons moving through wires, we can use particle concepts, discrete charges flowing from place to place. This works beautifully for most purposes. But when we try to understand what's happening at a deeper level, when we examine individual electrons or think about how transistors actually function or consider what's happening inside an atom, we need wave concepts, interference, superposition, probability amplitudes. And we need to remember that neither picture is complete or fundamental. They're both approximations, both ways of translating an underlying quantum reality into language and concepts we evolved to handle macroscopic objects. A wave function itself, that mathematical object that describes quantum systems, isn't a wave in physical space. It's not like a water wave or a sound wave. It's a wave in an abstract mathematical space called Hilbert space, and it encodes probabilities, the likelihood of different measurement outcomes. When you measure a particle's position, the squared magnitude of the wave function at each point tells you the probability of finding it there. The wave function itself isn't something you can directly observe. It can only see its consequences, the statistical patterns it produces when you perform many measurements. And this is why complementarity is so fundamental. You can prepare electrons in a state where their wave nature is apparent, where they create interference patterns, where they behave like extended waves. Or you can prepare them in a state where their particle nature is apparent, where they have relatively well-defined positions and momenta, where they behave like localized objects. But you cannot do both simultaneously. The experimental arrangement that reveals wave behavior necessarily obscures particle behavior, and vice versa. It's not that one aspect is more real than the other. Both are equally real and equally necessary. And the fact that they seem contradictory tells us something profound. Our classical concepts, built from millennia of experience with large objects, are fundamentally inadequate for describing atoms. If you find this frustrating, if you want a clearer picture, a more intuitive understanding, I sympathize. We all wanted that. But nature doesn't care what we want. Nature doesn't care if we find it intuitive. The universe wasn't constructed for our comprehension. We evolved to hunt animals and gather plants and navigate social hierarchies, not to understand the behavior of isolated atoms. The fact that we can understand it at all, even in this strange mathematical language that violates our intuition, is extraordinary. We've managed to extend our knowledge far beyond the domain where our evolved intuitions apply. But that extension comes at a cost. We have to abandon the demand that everything makes sense in terms of everyday experience. Think about what this means philosophically. For thousands of years, humans assumed that the universe was fundamentally knowable, that if we were clever enough and studied carefully enough, we could eventually understand everything about physical reality. We assumed there was an objective reality out there, independent of observation, and that science was the process of discovering what it was. Quantum mechanics tells us that assumption is wrong, or at least incomplete. There isn't always a fact of the matter about quantum systems before measurement. The act of observation doesn't reveal pre-existing properties. It participates in creating them. Subject and object, observer and observed, are inseparable in the way classical physics assumed. They're complementary aspects of a single phenomenon. This doesn't mean reality is subjective or that physics depends on consciousness. The mathematics of quantum mechanics is completely objective. The wave function evolves deterministically according to Schrödinger's equation. The probabilities are objective features of quantum states. What's different is that these probabilities aren't just expressions of our ignorance, as they are in classical physics. When you flip a coin, it has a definite outcome even before it lands you. Just don't know what it is yet. The probability reflects your ignorance. But when an electron is in superposition, passing through both slits simultaneously, there isn't a fact about which slit it went through. The probability reflects a fundamental feature of reality itself. Only when a measurement occurs, when the quantum system interacts with a classical apparatus in a way that could reveal information, does one outcome become actual. And here's something even stranger. This happens instantaneously. When you measure the position of an electron, its wave function collapses everywhere simultaneously. If the wave function was spread across the meter, the collapse happens faster and light could travel across that meter. This troubled Einstein enormously. He called it spooky action at a distance and saw it as evidence that quantum mechanics must be incomplete. But experiments have confirmed that this really happens, and it doesn't violate relativity because no information is transmitted. You can't use wave function collapse to send signals faster than light. It's a correlation, not a causal connection. The mathematics that describes all this is remarkably simple and elegant. Quantum states are vectors in Hilbert space. Measurements are represented by operators. The probability of a measurement outcome is the squared magnitude of the inner product between the state vector and the eigenvector corresponding to that outcome. The time evolution of the wave function is governed by the Schrödinger equation, a beautiful piece of mathematics that tells you how quantum states change. None of this mathematics contradicts experiment. None of it produces paradoxes when you calculate carefully. The paradoxes only appear when you try to translate the mathematics back into classical language, when you try to tell stories about what's really happening using concepts like position and trajectory that simply don't apply. And that's the final lesson I want to leave you with. The history of physics is in large part a history of discovering that our intuitions are limited. We thought the earth was flat and stationary. It's not. We thought space and time were absolute. They're not. We thought particles had definite positions and velocities independent of measurement. They don't. Each of these discoveries required abandoning something that seemed obvious, something that contradicted all everyday experience. And each time the new understanding was more powerful, more predictive, more useful than what it replaced. Quantum mechanics is the most successful scientific theory ever created. It explains chemistry, explains how atoms form molecules, explains the periodic table, explains the sun's energy source, explains superconductivity and superfluidity and countless other phenomena. It allows us to build lasers and transistors and quantum computers. It's been tested in millions of experiments over nearly a century and it's never been wrong. Not once. Every strange prediction it makes has been confirmed. So when someone tells you they understand electricity, ask them this. Do you know that the electron doesn't have a position before you measure it? Do you know that it's simultaneously wave and particle, and that both descriptions are necessary and neither is complete? Do you know that complementarity isn't a limitation of our knowledge, but a feature of reality itself? Because if you don't know these things, you don't understand electricity. You understand an approximation, a classical shadow of what's actually happening, and that's fine for most purposes. You don't need quantum mechanics to wire a house or design a circuit board. Classical physics works beautifully for those applications. But if you want to understand what electricity actually is, what electrons actually do, you need to accept that reality at the quantum level is fundamentally different from anything in our everyday experience. You need to accept that wave-particle duality isn't a contradiction to be resolved, but a complementarity to be embraced. You need to accept that measurement isn't passive observation, but active participation in creating reality. This is uncomfortable, I know. We all wanted classical physics to be right, to be fundamental. It's so much cleaner, so much more intuitive, so much easier to visualize. But nature doesn't care about our preferences. And what we discovered, what decades of careful experiments forced us to conclude, is that the universe at its most fundamental level is quantum. The classical world emerges from the quantum world, not the other way around. And understanding this, really understanding it, changes how we see everything. Because once you realize that reality itself is probabilistic at the deepest level, that superposition states really exist, that the act of measurement creates the properties it measures, you can never look at the physical world the same way. Every electron in every wire is a quantum system. Every photon of light is a wave and a particle. Every atom is a probability cloud of possible states. And all of it, all of this quantum strangeness, averages out into the solid, definite, classical world we experience, not because quantum mechanics stops applying at large scales, but because measurement becomes so frequent and true that superposition can never establish itself, that uncertainties become negligible, that the wave function effectively remains collapsed. We are not observers standing outside nature, looking in. We are participants, made of the same quantum stuff as everything else, subject to the same rules, embedded in the same wave functions. Our measuring devices are quantum systems too, just very large ones, where classical behavior emerges from quantum foundations. And this participation, this inseparability of observer and observed, is what quantum mechanics reveals. Not as metaphysics, not as philosophy, but as experimental fact, as mathematical necessity, as the only way to make sense of what we actually see when we probe atoms with enough precision. So yes, electrons are both waves and particles. Both descriptions are needed. Neither is complete, and that's not a flaw in our theories or a gap in our understanding. That's the nature of reality itself. Physics has given us the power to manipulate individual atoms, to build technologies that would have seemed like magic a century ago, to understand the sun's light and the stability of matter and the colors of flowers. But it has also shown us the boundary of what can be understood, the point where classical concepts break down, where language itself becomes inadequate. And perhaps that is the deepest lesson of all that, even in our greatest intellectual triumph. Even in quantum mechanics, we find not final answers, but new questions, not complete knowledge, but a framework for acknowledging what cannot be known. The universe is stranger than we imagined. It's also more subtle, more elegant, more mathematically beautiful than classical physics ever suggested. And somewhere in that strangeness, in that irreducible quantum fuzziness, in that complementarity that refuses to be resolved, lies the deepest truth we've discovered about physical reality. Not that everything is knowable, but that some things aren't. And that's exactly as it should be.